Okay, hello everyone. Uh, Welcome to today's lecture. Uh, Let me start from the point where we left. Let me give you a recap and then we can start our today's lecture slides after that. So basically, we were talking about how we can view an operating system, and we said like, okay, there are three different views, three different angles, which we can look at look an operating system. First, the services which are offered by an operating system. Second, the user interface which is provided by the OS, and third, how the components of an operating system are connected with each other. That is interconnection of the OS components. So we covered the first two parts, that is basically about what are the services offered by an OS and what is a user interface. Now, the services which are offered, those services are actually provided to the user program or applications through system calls. So whenever an application needs a service, it makes a system call. To get that service. And these system calls are frequent. If you remember, last time we had seen this example where we actually observed that even in a simple task of copying that all of the data from a source file to destination file, there are so many system calls that are involved. Yeah. So this is like calling a system call is a frequent event in the lifetime of an application. And the other thing that we stated was like applications, they don't make the system calls directly. What they do is that they use an application programming interface to invoke the system, which eventually trigger the system calls. And why we use this application programming interface? To achieve the portability, which basically means like if an application is written by one person at a system, then the same application can be used on another OS, provided that both OS implement the same application programming interface. So using APIs is like more user friendly, and also in the sense like it reduces the error or it makes the program writing less error prone. Okay. And then we saw an example of a standard API, like for example, the read function, where you provide as parameter your program, which is calling this API and needs to provide the file descriptor uh, of the file from which it wants to read the data, the buffer, which is basically a memory location where the data will be stored after it is read from the file, and the count, which is the amount of the data that needs to be read. So, so until this point, if you have, so this is what we have covered until the last lecture. So if you have any question, let me know, and then we can start our today's slide. No? Okay. So the question, remember we said like when we are writing a program, it's preferable to use the APIs functions instead of calling the system call directly. Why we should prefer to use the API functions? Uh, because it makes the life more easier for the programmer, and it is less error prone. So for example, let's say you have a user level program and it makes an API call with the name of open. So when you make this program, so when you make this function call, so then the API library is invoked, which then will invoke another, which will then in turn invoke the system call. So basically the flow of control is like first you invoke the API in your program, which gives the control to the API library, which then ultimately calls the system call of your operating system. And this actually becomes more easier, as we will see in an upcoming example, that how making the API makes it easier for the programmers to write their code. Uh, okay. So here is another example of like when you are writing a C program and in your program you invoke the printf. So printf is a function of the library or API call, and this API call then ultimately calls the write system call. So here is like we are writing, for example, printf in our C code, which basically mean that we want to write something on the output device. So since user applications, they cannot directly interact, or they cannot directly send data to the output devices, or cannot read also from the input devices. So that's why their control is actually directed to the standard C library, which is an API library. And then this standard C library actually internally implements the code for the printf function. And in the body of the code of the print in the body of the code of printf function, actually the write system call is invoked, which as a result finally traps into the operating system, which provides the service to write data to an output device, which is in this case the screen or monitor. So here is an example of like how using the API functions make the life easier. So let's say we are writing a program, and instead of trying to do printf this time in the user program, we actually directly want to call the system call. So if we want to do that, then we have to write this system call here. So when you are writing this, then you need to provide. Last time you were providing only the string which you wanted to print on the output device, and then the API takes care of all other things. For example, the file descriptor and the size of your string. But if you don't want to use printf, which is an API function, then you can also directly call the system call, but then you need to remember other things. For example, you need to provide the file descriptor, which is basically in this case the file descriptor for the output device. So you need to know it. Uh, and then the string which you were anyway providing also in the case when you were using the printf. But on top of that, you also need to provide the number of bytes you want to write to the output device, or actually the size of the data in terms of number of bytes. So here basically you need to specify more input parameters, two more parameters as compared to the printf. So if you make mistake in providing any one of them, then either your system call will not work, or it will work but it will not print what you actually wanted it to print. For example, if you instead of 13 you specify here 10, so it will not print all whole of the string. Or if you provide here uh, some other file descriptor ID, for example 2, then maybe the data will not be directed toward the output device, in this case, which is screen. And this was basically the hello.c version of the user program, and this is hello.s version of the program. So when it is converted into assembly, then this will be actually replaced by the syscall instruction, which will end up in making the system call. And one more thing is like uh, when you convert your higher level language into assembly program, the type of the instructions which are created, or which are like which replace the which replace the C language, those instructions are dependent upon the underlying hardware platform. So for example, if you are using ARM processor, then the set of the assembly instructions will look different as compared to the case of like if your machine is using the Intel processor. So it also depend upon your hardware, what CPU is available on your machine. If you put extra bytes in the instruction, would it just take up mm, unnecessary null space? Are you referring to this write instruction on the sorry, write system call on the left side of the slide? The 13 byte instead said 15. Just an unnecessary null space. Yeah, so it was not null space, but whatever you have in your buffer there. So you are actually providing the address of the buffer. So, and you are saying that you actually wanted to copy 13 bytes from that buffer, because you know that 13 bytes actually contain your valid data. But if instead of 13 you write 15, so it will copy that data from there, but then after 13 byte at location 14 and 15, it will copy whatever garbage is there. But again, then we are assuming that this is the situation when there is no protection against this buffer overflow kind of approach. So this is normally known as buffer overflow, which is kind of vulnerability, but we are not going to discuss it here. But if there is no protection against that vulnerability, then it will print that garbage. Okay, some other student also had a question. So printf automatically interprets the necessary parameters to generate a write system call. Yeah, that is correct. So it is not printf. Yeah, printf automatically, because the implementation of the printf in API is such, in the API library is such that the library prepares the other remaining parameters like the file descriptor and the size of the data to be written. Okay, we have already seen this slide. So like, for example, how your API and your OS interact. So for example, in user application, you are making an API call, or you're calling a function of the API library. So for example, let's say it is open. The name of that function is open. So so then, as a result of the calling that API function, you will at the end of the day, you will trap into the system call interface. Now, how do we know? How does the OS know that which system where is the code of the system call which it wants to which it needs to invoke? So for that, we use actually the similar approach as we used with the interrupt service routine our interrupt handling. Remember, in interrupt handling, what we were doing, we were maintaining a table, right? We were maintaining an interrupt vector, and then in the interrupt vector, what we had for each location the address of the interrupt service routine for that particular interrupt, right? So we do the similar thing here. So whenever, for example, you are making a system call, so each system call has an ID. So based on that ID, you look into the to the table. So let's say if your ID is I, so you go into the entry I of the table, and that entry actually provides the address to the location where body of that system call is implemented. A code of that system call is written located in the memory. So then control transfers to that memory location. So for example, here you are making the open call. So then it has an ID, for example, I, then you make an entry into this table, system call table. It will give you the address where the open system call is implemented. You will go to that location in memory, start executing, and after that you will return, and returning when you go back to the point where you will actually to the next instruction after you had made the open function, you had called the open function of the API library. Okay, now we have seen that how the user applications normally they interact with with the system calls, or how they invoke the system call, not directly but through libraries. Uh, but what if we need to pass parameters to the system call? For example, just like we have seen in the previous example, like if in the user code you are making a system call, right? So you need to pass the parameters, right? So we need not only the name of the system call which we need to make, but also the parameters which need to be passed to that system call, right? So there are three general methods to pass those parameters to the OS. One is like the simple method is that you can pass the parameters in registers. So for example, if you are making a system call, let's say S1, so difficult to write here. Okay, so let's say if you are making a system call S1, and it takes three parameters. So what you will do is like not you actually, as a programmer, you will not do that. But when you make the uh, call for the function of the API, as a part of that call handling, what will be happen that your parameters will be copied in the registers of the processors, And then when the code of the system call is invoked, then inside that code, those registers will be read. So your parameters will be made available to the system call in that way. Okay. But in some cases, it may be the case that number of the parameters which you want to pass to the system call, they are though they are more than the number of registers, or maybe the registers are not available, they are already occupied for some other purpose. So in that case, how can we pass the parameters to the system call? For that, what we can do is that we can store the parameters in memory. We can store the parameters in a memory block or a table. And then what we do is that instead of passing all those parameters through the registers to the system call, we just place the address of the uh, memory block or table in a register. And then the system call can read that address, and it can find out, okay, this is the location where all the parameters are located. So, for example, in the first approach, what we were doing is, let me go back to Notepad, OneNote, sorry. Just give me 1 minute. So, for example, let's say this is your user program, and you are it doesn't matter whether you are directly invoking the system call or you are using the API. Let's say even if you are invoking, even if you are like making the system call directly. So let's say you are making the system call, right? So it takes three parameters, right? We have seen in the previous slide. So if it takes three parameters, then the first approach of like passing the parameters to your system call is like you have registers. Let's say I'm just um, making up some register names like R1, R2, R3. And in those you will put the values of parameters, let's say parameter 1, parameter 2, parameter 3, right? So actually the call handling will take care of this. So this will be copied in the registers, and when on the other side the body of the system call is executed, so then what happens that it will first check these registers and read these values from the registers, and then treat them as input parameters, and then after that it will execute the body of the system call, whatever it is, right? Now, the other cases like where we have larger number of parameters, and so we cannot put them in the registers, or registers are not available. So in that case, what we do is like on this side, on from the user's perspective, what happens is that in the memory, you have a location, let's say any particular location, and in there you put those parameters, you save those parameters in memory P1, P2, and P3, and you have the starting address of this memory location. Let's say starting address is SA, right? So then in the register, let's say this time again R1, you put the starting address, and then when control goes to to the system call, it only looks at the system address. Not system address. What was this? Starting address. It gets the starting address from the register one, and then it finds the parameters from that memory location. So it can now read from this memory location right here, and it can get the values P1, P2, and P3, and then use them as required in execution of the rest of the body of the system call. So this is how things are working here. So the good thing about this approach of passing the parameters through memory is that there is no limit on the number of the parameters, and because the memory is much larger in size as compared to the number of registers in the register file, so we can support practically unlimited number of parameters. Okay, so this is just graphical depiction of what we have seen in the previous slide. That on the user side, you have a user program which want to make a system call, but the system call needs some number of parameters. So what you do, the first approach is that you load so the second approach is that you put the parameters in the memory location X, and then you load the address of X in the register, and then you make the system call. So when you make the system call, the control is transferred to the operating system. The operating system first uses the parameters from the table X, because now it knows the address where is the table located, and after that it starts executing the body of the system call. Oh, sorry, I was going back. Okay. Uh, as we have seen in a very small example previously, where we were trying to copy content of one source file to a destination file, we found out that there are a large number of system calls which are invoked, but though all of those system calls were related to a particular subset of system call, which was basically about file management. But there are system calls also falling in other categories. For example, process control, which basically help us to create a process, to terminate a process, to create children of a process, to pause a process, and so forth. Similarly, for file management, we have system calls for creating files, for deleting files, for reading from files, reading or writing to them, or for example, changing the cursor position in the file, and many other file related system calls are there. Similarly, there are file calls for device management, for example, reading, writing data to the input or output devices, the information maintenance, for example, how many processes are running currently in your system, and like for example, how many of them are user level processes, and so on and so forth. Communication, which is basically about exchanging information between two processes. So for that, we also need the system calls from the operating system, because uh, operating system is involved in the communication. Doesn't matter what is the mode of communication. Actually, there are two major mode of communication. One is known as the shared memory based communication, and the other one is message passing. But in both cases, you need to interact with the OS, either to set the shared memory or to exchange the messages. And similarly, protection, like for example, if there is a file, then who can access those files, and also what kind of operation can be performed on a file. Even if you have an access, then what type of access you have, whether that file is executable or not. So all these things, all these services, they are provided through the system calls implemented in the code of the operating system. So here are some examples of the system calls in Windows and Unix operating system. Uh, to be honest, I am not that much familiar with the system calls in the Windows, but they are, yeah, self-evident, like they are clear that what they are doing from their name. So for example, you have for process control in Unix, you have system calls like fork, exit, and wait. So you also have their counterparts in Windows, like create process, exit process, and wait for single object. So similarly, for file manipulation, you have open, read, write, close, so on. You don't need to like remember these system calls definitely, but this is just an example. Like for each type of service or a domain, for each type of resource management, you have system calls implemented in the OS to make those services available to the user applications. Okay. Uh, System programs, they are actually provide a convenient environment for the program development and execution. They help us as a user to manage the system, and you can like divide it into several categories. For example, file manipulation, status information, file modification, and so forth. This is not important for at this time at time point for us, but when we will go, we are not going to cover anyway file manipulation in operating system one, but later on in operating system two, if we are going to cover, then we can talk about more about them in the second phase of this course. Okay, so I'm skipping these slides. So let's move to this slide where we basically are talking about how uh, a source file or a source program is converted into a executable file on a system. So what is the role of the linker and loader in this whole process of converting a source file into an executable file? So the first thing is like when you write your source program, for example, in main.c, let's say it is your uh, application or the program. So first you feed it into the compiler. For example, you can use GCC compiler on Linux or Ubuntu, and it will convert your main file into the object file, the source file into the object file. But then if you have multiple source files in your project or in your application, then you will have multiple object files. And then it is job of the linker to link all of those object files together to create a single executable file. Hmm. And then the job of the loader is basically this executable file is then created by at this point by the linker by linking all the objects files together, but this is still a file and it is simply residing in your disk. So if you want to run that executable file, you must first load it into the memory, and that is the job of the loader module, which moves your file into the memory. And at the time of the loading, uh, it may it may link other library files with your program. uh, so library files, they can be linked with your executable in the two different ways, either statically or dynamically. So statically basically mean that they are linked uh, before your before your file is actually executed. On the other hand, dynamic linking is the situation where you link the library files with your executable at runtime, which means that if your executable a file or your a process is actually using a function from a library, then that library will be linked with your executable. But if it is not using, then it will not the library will not be linked with your uh, executable file, which basically is more advantageous because the if you are not using any function from the library, then there is no point in linking it to your executable, which basically reduces the size of your executable program, right? ELF format, actually it is executable and link. It stands for executable and link format, linkable format, and this is the format of your executable and object files in Linux. So if you use these two commands, or if you go and look for the documentation of these two commands, read ELF command and object dump command, they will help you to understand the first command, read ELF. So this command actually helps you to read the executable file or linkable file, objects files in your Linux system. So you can this command will present those files in human readable forms, and will give you information about different sections within your executable file. On the other hand, the object dump command, it comes with different switches or with different options, but basically you can use it to convert your object file into assembly file. or also you can either use you can provide the options such that this command will actually convert your object file into the assembly file along with the equivalent higher level code. Like for example, if you are writing printf, you in your program you had printf and you don't have now your source code, you only have your executable file available, then you can use object dump, and now it will show you the assembly and also its equivalent high level code, which is printf in this case. Okay, so previously when we were talking about APIs, we said that one advantage of using APIs is that uh, they make our programs portable. That's true, but not completely true. Why? Because if you are, let's say you wrote a program using a particular API, let's say standard C library, uh, and you are running your program in your system, and definitely it's mean that the standard C library is available in your system and is compiled and linked with your program, right? Now, if I borrow the same program for you from you, actually the executable of your program, and run it on my system, I will be able to run it only if my operating system has implemented the standard C library, right? If the standard C library is not supported on my system, then I will not be able to run your executable file. So that is that like mean that is a level of portability which is available. But what if that standard library is not supported on my system? In that case, I will not be able to run your program, so it will not be portable anymore, right? So apps compiled on one system, they usually are not executable on other operating systems. So each operating system provides its own unique system call. So this is the basic reason why if you have, let's say, compiled an executable file for Linux, then it will not be able to run on Windows, because if, let's say, you are making a system call fork to create a new process on Ubuntu, but now that fork is not available on your Windows operating system. So exactly same thing you can do, but on the Windows, but the name of the system call is different, right? So it will not recognize the fork system call, right? So each operating system provides its own unique system calls, and also not only that, each operating system has its own file format. So remember in previous file slide we talked about readelf command, which enable us to read the object file or executable files in Linux or Ubuntu, but they have their own format specific for these Linux systems. Now, if you if you have the same executable file and move it to the Windows, then Windows use a different file format, and it will not be able to read it, right? So as a result, you will not be able to execute. You will not be able to run your executable file on the Windows. So there are like two issues. Every operating system has its own system call set, and they also use separate file formats. However, still we can uh, uh, make the applications run on multiple operating systems. But for that we have some restrictions. If we have written our application in an interpreted language like Python, and the interpreter of that language is available on the operating system, then we can run the same application on different systems, right? So for example, if I have written my application in Python and the interpreter of Python is available on both Windows and on the Linux, then it will be fun for me to run the executable on both of them, because interpreter is available. So it will interpret actually uh, my executable file on the Unix, considering that I'm running on the Unix. So it will translate those system calls uh, which I'm making in my executable to the equivalent system calls in the Linux system, and when I will run it on the Windows, it will translate the system calls to the equivalent system calls of the Windows operating system. Another option is that you can write your application in a language that includes the virtual machine, for example, Java. So have you guys taken course on Java programming? Like, I don't, I cannot see you guys, so I was like, uh, okay. Okay, some people have. Yeah. Okay. Yeah. Okay, someone asked a question. Sorry, I didn't see it earlier. So it says interpreters are built different in each operating system, right? Since it needs to know the specific function. Yeah, that's correct. That's why they are known as interpreters. So the thing is, like, on one side you can have, like, you can assume it just like a person who knows so many languages. Like, let's say there is a person who knows French, Italian, Spanish, English, Persian, right? And now if I am of if I know only English, so that person can translate whatever I'm talking to the audience who can speak only Spanish, Italian, French, or Persian, right? So my whatever my speech is, it will become understandable to Italian audience, French audience, Persian audience, and so on. So the same is the situation here. So if your interpreter uh, s- is ported on, let's say, on Windows, Linux, uh, Solaris, or any other operating system, and you have written a Python program, let's say, on using Linux, so the same Python program now can be interpreted and can be run on Windows or other operating systems. And then the worst option is, like, the standard language. You write your program in a standard language like C, and then compile separately on each operating system to run on each of those operating system. So, which basically mean that you cannot use your executable file. You have the source code. Let's say you want to run it on the Unix, you first compile it on the Linux, and then you run it on Linux. Now, if you want to run the same program on Windows, you must have the access to the source code. You compile that source code on the Windows, and then you run it on the uh, and then you run it on the Windows platform, right? But again, we are assuming, like, you are using the appropriate API functions. Uh, okay, so the application binary interface, it is basically an architectural equivalent of a API, just like we say that what is the job of the API? The job of the API is to uh, translate the functions call made in the user program to the correct system calls for a given operating system, right? So same is the case for the application binary interface. So basically, uh, its job is to provide an interface between different components of the binary code for a given architecture. So, for example, let's say you are writing a program. Actually, we have. Let me go back. In this slide, our next previous set of slide, we had an example. Okay, let me go back to the previous set of slide to just explain what I mean. Where was it where we had an example about a right? Yeah. So here, so you are like here we are directly making a system call, right? Uh, Okay. So here we are directly making a system call, and this is our program written in hello.c, like C language, high level language. Now, when we convert into the assembly language, it is converted into the assembly instructions here. But the type of the instructions which are generated, it depends upon your underlying hardware architecture. As I guess I mentioned it earlier. So if you are using, for example, mm, for example, if you are using ARM, a different set of instructions will be generated. If you are using Intel, a different set of instructions will be generated for the same application. So just to draw a parallel between API and ABI. So API is actually, so this is your API and it is your interface. On this side, you have user program. I'm just writing UP for user program. right? And here you have your operating system. Now, uh, in operating system, let's say you have Linux, and Linux provides the support for this API, right? Whatever API it is. Actually, it is a library. So let's say Linux provides support for this library, and let's say Windows also supports this particular library or API. Now, this user program then can run on both Linux and Windows, right? But there is an other level. Let's say we only talk about Linux. So in Linux, then when you are running this program, you are converting it to the assembly, right? But is the machine on which you are running your Linux system, does it have a ARM processor or does it have a Intel processor, right? If it has Intel processor, a different set of instructions will be assembly instructions will be generated. If it has ARM processor, a different set of assembly instruction will be generated, right? So this is known as ABI or application binary interface. So which basically mean like uh, if you have the same API supported on different systems, but then the underlying hardware is different, then it will be no, you cannot run your binary as it is, right? So if you have like a machine on which you are running Linux, but the processor itself is Intel processor, and you have the binary, you are running on it on this machine, and then you move it to another machine where again you have the Linux operating system, but your processor is, let's say, ARM, then you cannot run the same binary as it is. You need to again compile it. Okay, so this brings us to the third part of our a third view about how we can look at the operating system. So we can talk about the different components an operating system have and how they are interconnected. Or we can talk about the internal structure at very high level, the internal structure of the operating system. So depending upon the internal structure, you can divide operating system into different categories, like monolithic structure, where you have this one big piece of code taking care of everything. Layered approach, where you have separate layers for performing different jobs and then clear interface between those layers. Microkernel approach, where what you do is that you want to reduce the size of the kernel. So what you do is like you put in the kernel only the most essential components of the operating system, and everything else you move it out and you implement it either it as a system service as a user or as a user level application. Module approach is like where you develop your operating system in modular form in such a way that you can plug in the modules at runtime. Okay, so let's talk about monolithic structure. So the main feature of this type of operating system is that you have a functionality of kernel which runs in a single address space. So you have like this big piece of code, big chunk of code, which implements everything, all the functionalities, required functionalities of the operating system within a single address space. So single address space mean that as a single process. Each process just keep in mind that each process has its own address space. So one process cannot access the address space of another process. So if we implement everything, all the functionalities, all the modules in a single address space or as a single process, then it's mean that different component of the operating system can easily interact or access each other because they are actually part of the single process. So here is an example of monolithic structure of an operating system, which is in this case Unix OS. So if you look at this figure on the right side, we are dividing the operating system into two parts, one which is named as kernel and everything else. So in kernel, you are putting so much functionality. For example, you are putting file system management, swapping block IO, disk management, CPU scheduling, page replacement, demand paging, and so much more. So this is like a lot of functionality put in a single piece of code or in single address space. So the kernel is basically consisted of everything below the system call interface. So on the bottom side, you have hardware components. So your kernel is responsible to interface with these hardware resources of your machine. On the other side, on the top side, you have users or other applications, or user level applications, which actually then use system level processes or services to interact with your operating system. For example, shell commands, compilers, and interpreters or libraries. So the main point is like in this approach, you put a large number of functions in a single level of the operating system called kernel here. So the good thing about this approach is that it is your communication within the kernel is fast. Communication within the kernel is fast because all this code here is implemented as a single process. Everything here is implemented as a single process. So if there is a need to exchange information between one part of the kernel, let's say file system or file handling and the CPU scheduling, this can be done relatively easier and the communication will be fast. The problem is that this approach is tightly coupled, which means like if you want to modify one functionality in the kernel, you may end up missing the other other functionalities offered by the kernel, or they get broken and they will be not working. So it is difficult to modify and difficult to debug your source code of the kernel if you are making any changes in the kernel. Let me check the time. Okay, we are going good today. Okay, so the other approach is like where you can have monolithic structure, but you can add modules. So all functionality of the kernel, it still runs in a single address space, but you have the modular design. And as a result, what happens that you can easily modify your operating system and are actually the modules of the operating system. And you can also develop a new module and you can plug that module in the kernel or in the operating system at the runtime. Actually, uh, we are going to have an our first project about this loadable kernel module. Don't be scared. It will be something very easy. But I just want you to get familiar of the fact that we can develop kernel level modules and then we can load them in the kernel at runtime, and then they become available for use to our user level applications. So this is how graphically this approach looks like. You have applications above the system call interface running. They use a standard library, for example, standard C library in case of Unix. This standard C library is supported on all major operating systems. So these applications then use this library to invoke system calls and then interact with the kernel, but or with the operating system. But if we look into the kernel itself, you have different modules taking care of different services or different functionalities. Like you have a separate module for file system, separate module for CPU scheduling, and a different module for memory management. And then at the bottom you have the device drivers which allow you to interact with your hardware. So if you compare it with the previous figure here, we had all the functionality implemented in a single uh, process address space as a single code base. But here you have the more modular approach, and as a result what happens is like your source code of the kernel, it becomes more manageable. And if you make changes in, let's say, in one module, it is uh, it is less of the case that it will change, make unwanted changes in other modules or other parts of the kernel. Okay, layered approach. So this is the third approach, or third way of constructing the operating system, or designing its internal structure. Here, what we do is that we divide the operating system into a number of layers. And then each layer is built on top of the lower layers. So, for example, the bottom layer here is your layer, or layer zero, and the highest layer is your user interface. So in between you have so many other layers. Uh, with modularity, what we do is that layers are selected such that each uses functions and operation of only the lower level layers. For example, for layer one, it will use the services of the layer zero or hardware, right? So basically, layer one will be drivers, your device drivers, which are basically piece of software. So they will interact with the hardware. Now, if any user want to read or write to your hardware devices, so it will interact with your layer one, which are your device drivers, right? But it cannot directly go and control or interact with the hardware. So every upper layer can only use the functions or the services provided by the lower layer, and every lower layer provides you functions or services to the upper layers. The good thing about this approach is that it's easy to debug each layer independently. So if, for example, there is you are making some changes, let's say in layer X, and then you, after making changes, when you run it, you see that your kernel is broken. But maybe yes, it is broken, but then the good thing is that you know that the changes are only in this layer, and they have not affected in any layer above or below the layer where you are making the changes. Sorry. Also, each layer hides the internal implementation details. So, for example, and if an upper layer is asking for services from the lower layer, it doesn't need to know any details. So, which means that irrespective of how the internal coding is done or how our layer is implemented, as long as it provides the agreed upon services to the upper layer, it will be fine. Which gives you freedom to how to implement a particular layer. But the bad thing is that the user program, it needs to traverse the multiple layers to receive the OS services. So for example, if user program is running at the uppermost layer and it needs to interact with the hardware, then it needs to traverse all these layers, and traversing each layer is expensive because each layer is implemented as a separate address space. So how can we avoid this? How we can like mitigate this downside side of the approach where a user program needs to traverse multiple layers? So what we can do is that we can reduce the number of layers by putting more functionality in each layer. So actually making each layer fatter or thicker, but then reducing the number of the layers. So we will still have some level of modularity, but at the same time we will reduce the number of layers, and as a result, our user program will not need to traverse as much number of layers as in the first case. Okay, microkernel system structure. So this is an approach where uh, basically the idea is same as the modular approach which we have covered earlier, but the thing is that uh, our focus is on reducing the size of the operating system itself, or the size of the kernel itself. So what we do is that we move as much of the functionality from the kernel outside into the user space. So for example, uh, traditionally all of these functions, all of these functionalities, they were offered as in the kernel code or as a system level code. For example, file system management and device driver. Now, but as a part of the microkernel approach, what we do that you keep only most basic services like interprocess communication, memory management, and CPU within the kernel domain. And then you implement the other services like file system and device manager as user level applications. Now, however, the application programs, they cannot directly interact, or they cannot directly ask for services from file system management or from the device drivers. They can request services from these components by only sending messages to them through your microkernel. So this is the way how you can communicate. Even these components which are implemented in user mode, they cannot communicate with each other directly. They can communicate only through the microkernel, which means that they need to switch the code space, like from moving into the user space to the code space to the kernel space, which is expensive. Why it is expensive? Because every time when you switch the space, either from user space to the kernel or from kernel to the user, the context switch is happening. And when context switch happening, you need to load so many registers. You need to save them in memory. So you need to also uh, uh, restore some other registers from the memory by loading their values. And at the same time, you also need to clean your caches and your TLBs, translation look aside buffers, which is expensive and it takes time. That's why we say that whenever you make a switch from user space to the kernel space or vice versa, it takes a huge amount of time. And that's why also system calls are also expensive. So the good thing about microkernel system structure is it is easier to extend a microkernel. Why? Because as compared to the monolithic approach, the size of the kernel is much smaller. So it is easy to manage the code, and if you are making changes or modification, it is relatively easier to track them. It is also easier to port the operating system to new architectures, because when you are like porting to new architecture, let's say, then you maybe need to write new device drivers. For example, then you need to implement only this part, the part which is written as the microkernel. You need to re-implement only for the new architecture this component, this part of the kernel, not everything, unlike the monolithic structure of an operating system. Since you have less code, relatively the size of the code is smaller, which means that your code is more secure, because larger the size of the code, potentially more vulnerabilities are there, which can be then exploited by an attacker. uh, or maybe there are more bugs, programming bugs, because if you larger the code, there is more chance of doing the programming bugs when you are developing the code. The bad thing is there is performance overhead of user space to kernel space communication, because uh, every time if an user program needs the file system management related service, it first need to send the request to the kernel, and then kernel will forward request to the file system management component. Same is the case when an application program need to read or write data from a device. So this becomes expensive as compared to the case where file system was part of the kernel itself. Then there will be no, there will be only a single uh, uh, crossing of the boundary between user space and kernel space. But here it becomes you cross the boundary twice. First from the application program to the kernel, and then from the kernel to the component which is implemented in the user space. So modular approach, this is the last approach which we are going to discuss, and is used by most modern operating systems. Uh, and this approach basically implements loadable kernel modules, which basically mean that you can develop a module, and at the runtime you can load into the kernel. So each component is separate, clear from the name of the approach itself, since it is the modular approach. So you have a separate module for every functionality of the operating system. However, the modules, they can talk to each other over known interfaces. Uh, and each module is then loaded by the kernel as needed. So if we compare this approach with the layered approach, there are some similarities. For example, each module has a defined interface. Just like in layered approach, every layer has a defined interface to provide services to the upper layers or to receive services from the lower layers. Uh, Similarly, the difference is that uh, here each module can call any other module directly because they are implemented in a single user space, but this is not true for the layered approach where each layer is implemented as a separate process address space. When you compare with the microkernel approach, your similarity is that your primary module or kernel has only core functionality, just like in the microkernel approach where we implement only the most essential components as part of the kernel. So here also you do the same thing, and everything else which is not considered as most essential is implemented as a separate module with loadable module, right? The difference is when you compare it to the microkernel approach, the difference is that you do not need to invoke message passing for communication between different modules or different components of the operating system. So in that terms, it becomes less expensive. Okay, so with that, uh, we come to end of our today's lecture. It seems like it was relatively quick and faster. Actually, I wanted to keep it faster because we are lagging behind. We were supposed to start our chapter 3 or the topic of processes today, but we couldn't do that. And one more thing is like, since these first two chapters, chapter 1 and chapter 2, they are both like in their nature, they are introductory. They don't provide like too much detail about some particular functionality. So that's why I don't want to spend too much time today on explaining these things. Uh, is there any question related to today's lecture? No? Okay, if not, then we are done. I don't have any more slides for today. And
Cool.
on Thursday, we will start our topic about processes.
All right. Thank you.
Thank you. Have a good day.